So today we're going to move on from molar conversions between grams and moles and particles, and we are going to talk about gases and how we can do those conversions with gases. So first of all, so for molar volume, there's a mole volume relationship with gases that is really unique. So it's kind of so far we've talked about just like I said, going from grams to moles and moles to particles, and we can do that with gases. But there's another really cool thing about gases and how they behave, and this is actually what Avogadro is famous for. So for liquids and solids, the number of 1 mole depends on the types of atom present. But in gases, other factors such as temperature and pressure are factors that affect gases. And we know that, for example, if you blow up a balloon, let's say you go to the flower shop and you buy your favorite person a giant helium balloon, and they fill it at the flower shop, and you take it outside, and it's like one of our very cold Minnesota winter days, and you might notice that the balloon deflates a little bit, and it's because the gas in there, which is helium if it's a floating one, actually contracts and takes up less volume in colder temperatures. But if you take it back inside, it should kind of reinflate as the gas particles expand again with the warmer temperature. So we know that there's those kinds of behaviors with gases. And so for what we're going to talk about in this chapter, we're going to always assume that when we're talking about different gases, we're going to assume they're all at the same temperature and pressure. So standard temperature and pressure. So if you see this STP, standard temperature and pressure, that's what we're talking about. And what Avogadro, remember the Avogadro's number, the 6.02 times 10 to the 23rd, but he didn't really come up with that number, but he came up with a different, like, really important hypothesis. So we're going to talk about Avogadro's hypothesis and what that is. So when Avogadro states that equal volumes of gases at the same temperature and pressure, and that's key, it has to be at the same temperature and pressure, contain equal numbers of particles regardless of the size of the particles. This is because gases are mostly empty space anyway. That's why we can compress gases, and that's even why they compress themselves a little bit at lower temperatures. But it's because they're mostly empty particles. So that seems a little bit crazy, really, when you think about it, that, wow, it doesn't matter if I'm talking about hydrogen gas or carbon dioxide gas. If I have the same volume, so let's say 1 liter volume, I'm going to have the same number of particles of gas in there, the same number of molecules of gas in that sample, as long as they're at the same temperature and the same pressure. It doesn't matter that carbon dioxide gas molecules are much, much larger than hydrogen gas particles. It doesn't matter because, again, they're mostly empty space anyway. And the magic conversion factor, or the magic number, is, ding, 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 1 mole of gas at standard temperature and pressure occupies 22.4 liters. Always, as long as it's at standard temperature and pressure. Doesn't matter what kind of gas it is. If you have 1 mole of gas particles and they're not under pressure, they will occupy 22.4 liters. And because we know that to be true, we actually can use that as a conversion factor. This was an amazingly profound hypothesis when Avogadro discovered this, because now they had the ability to calculate, grams to moles and so on and so forth, but now we have the ability with a gas to know if I have a certain volume of gas at standard temperature and pressure, I can figure out how many moles of a gas I have. And if I know the volume and I can figure out moles, I can figure out how many particles, or I can figure out how many grams, and so on. Now you see why it's really important, and why even Avogadro's number, which he didn't discover but was named in honor of him because he was so important in pioneering some of these hypotheses and relationships in chemistry. So just a quick little visual to kind of demonstrate that. You're welcome for the artistic drawing here, but I'm looking at two volumes of gases. It's the exact same size square, or it should be. And if I count the number of particles, again, even though hydrogen is a much smaller particle, and argon gas is argon itself is a much larger atom, it doesn't matter, because see all this empty space in here? As long as these are at the same temperature and pressure, we're going to have the same number of particles. So, as I said, we can do those calculations that go between volume and moles now that we have this magic number of 22.4 liters contain 1 mole of gas particles. So since the volume of a gas changes with changes in temperature, again, we do have to specify that it's at standard temperature and pressure. So we're just going to assume everything that we are doing right now with gases is at standard temperature and pressure. Things get way more complicated, and we'll talk about that later in the year when we talk about gas laws, but we are not there yet. Standard temperature is 0 degrees Celsius. Standard pressure, so 0 degrees Celsius is right at that point where water freezes, right? So 32 degrees Fahrenheit. So 0 degrees Celsius and 1 atmosphere of pressure. Sometimes we express pressure in kilopascals, and some other like torr and other units too. But again, we don't really need to do a lot of calculating with this. You just need to understand that that's what standard pressure is. We're not going to be working with anything other than standard pressure, so don't worry about that. But if you see STP stated in a problem, just know it's just stating that, yep, we're at standard temperature and pressure, so we don't have to do any other extra conversions. All right, so 1 mole of a gas at standard temperature and pressure occupies 22.4 liters of volume, as we already kind of stated. Remember, 1 mole is this many particles. We've done those conversions already. So this is regardless of what type of particles are in the gas. It doesn't matter. And then we can use this as a conversion factor, and we can basically, with conversion factors, we could flip this either which way that we need to use it, with liters on top and gas on the bottom, or the other way around. So let's do a quick little calculation here. How many moles of water vapor are in a 50.5 liter sample of water? My path is going to be liters to moles, and I can and I only need that one conversion factor in order to do this problem. So I'm starting with 50.5 liters in my sample, and I want to know how many moles that is. So I simply set up using that conversion factor. I put moles on the top, 22.4 liters on the bottom. If I calculate this out, 2.25 moles. If I look at this, does this seem reasonable? Well, I have 50 on top, a little less than half of 50 on the bottom, so it seems like 2 point something. That seems like a really logical answer, so I think we're good. And if I wanted to take that same problem, 50.5 liters of water vapor, and I want to know how many particles that is, I simply need to use one more conversion factor. So I've worked through it down in the bottom, 50.5 liters of water, and this is water vapor, so the gas, and my first conversion factor is to get rid of liters, so 1 mole over 22.4 liters. But then if I want to get to moles, my path is liters to moles to molecules. Sorry, I wanted to find particles, which molecules. So now I'm going over here. I still have to go through moles. The magic mole. Everything has to go through moles all of the time. But yeah, I can set this up. So 50.5 liters of water, my first conversion factor, and then my second conversion factor. Yeah, I can use Avogadro's number over 1 mole So I'm going from here. So I'm starting here, going 1 mole over 22.4 liters to get to moles. And then I'm going using this conversion factor to get to particles, which remember is atoms, molecules, or formula units. And so that's kind of our new information on how to work with gas. Of course, we can always go in the other direction as well. What will the volume of CO2 gas be if there are 1.5 times 10 to the 25th molecules present in the sample? Then you just kind of work backwards. So you can start with molecules. We want to get rid of molecules, so Avogadro's number, which represents particles, goes on the bottom. That would cancel out. Then we have 1 mole. We want to get to liters, so we can use that gas conversion problem, putting liters on top and moles on the bottom, so things cancel out and we are left with liters. And I think that's it for this lesson.